Here you go. We are up. Hey everyone, welcome to the APAC 2020 Groundbreakers Virtual Tour by APAC OEC. This year, our event would be the biggest one ever done, 174 sessions, including normal sessions, workshops, and hands-on labs from 123 different speakers over 11 days. Also, it would cover sessions on 4 different technologies. Please remember to register as many sessions as you can, and all sessions would be available to replay as many times you want for 2 weeks after the initial date and time. You can also interact with speaker at any time during 2 weeks by posting questions and comments directly in the playback session page. And thanks to all the Oracle user groups, Java user groups, and to our sponsors, Oracle Groundbreakers and CloudDB, for making this event possible. With that, for today's session, we have Kaley, and speaking about SQL Tuning, Undocumented secrets for getting accurate cardinalities. And this session would last for 45 minutes. And if you have any questions, please feel free to update in the or ask questions in the Q&A chat tab in the webinar, and the questions will be answered at the end of the session. So without any further delays, I'll hand over to Kaley. Up to you.
Okay.
Yep.
Awesome. So let's get started. The name of the presentation is SQL Tuning, Undocumented Secrets for Getting Accurate Cardinalities. The very first thing that we want to talk about is the word undocumented. A lot of people shrug this off. They go, okay, it's undocumented, so what? That just means that it doesn't show up inside the Oracle documentation, right? And yes, that's also true, but it also carries some additional weight with it. Number one, it means it's not supported by
You
Oracle.
want to share your screen?
Yeah, am I not doing that? So sorry.
Yep. Sorry for that. Yep, thank you.
Let's see, how do I share screen? Screen 2, share. How about now?
Yes, but it's not in a presenter mode, it seems.
It's not in presenter mode. What do you mean by that?
I mean, we can see a half screen.
Half screen. How do I make it full screen?
Go to display settings, and then maybe you're in a duplicate monitor mode. So
okay, let's see. Share screen 2. Okay. Is this, you're not seeing this?
Same. Yeah.
Okay. What if I show you this?
You can maximize your screen, and then, yep, it's now good. Yep, it's good now.
Okay. Awesome. So, name of the presentation is SQL Tuning, Undocumented Secrets for Getting Accurate Cardinalities. The first thing we want to talk about is the word undocumented. This carries a little bit more weight than what a lot of people think. Some people think, okay, it's undocumented. That means it doesn't show up in the Oracle documentation. But it also means a couple of other things. Number one, it means that what I'm about to show you is not supported by Oracle support. And number two, it means that it can be changed or revoked at any future release without warning. So if you run into difficulties with this, don't go crying to Oracle support. And frankly, you shouldn't be using this in production. So with that said, the very first thing that you're saying to me is, hold on, Kaley, hold on. I came to this presentation to learn how to use these undocumented fixes. And the very first thing that you're telling me is don't use it. And that's not what I'm saying at all. These are actually extremely powerful tools to have in your SQL tuning arsenal, but you shouldn't be using them directly within your production code. Let me explain what I mean. It's a good idea to use this tool that I'm about to show you, these tools, to get the right execution plan. And then once you come up with the right execution plan, you want to ultimately use some kind of documented fix to enforce the correct plan. In other words, you want to use something like a baseline or a SQL patch or documented hence, etc. It would be a bad idea to find the right plan using these undocumented fixes and then directly implement these undocumented fixes in production verbatim. So the other thing that we want to talk about is cardinality, okay? Cardinality is the number of rows that Oracle expects to return from a particular step in an explain plan or an execution plan. So it's the number of rows that Oracle expects to return from a particular step in an explain plan or an execution plan. So if we're looking at a plan, we see a section called rows. That is the estimated cardinality that we're going to get back from each step in the plan. And cardinality drives everything. It drives your table join methods, whether you're going to be using nested loops, hash joins, sort merge joins, or merge join Cartesians. It drives your access paths, whether you're going to be using indexes or whether you're going to be ignoring indexes entirely, if you're going to be doing full table scans. It drives your join order. And if you have ever messed with any SQL tuning before, you know that join order is paramount to having excellent performance with your query. And the way that the cost-based optimizer in Oracle works is it works with cardinality estimates whenever it's creating a plan. And basically, the more inaccurate a cardinality estimate is, the more likely that the cost-based optimizer is going to do something slow, something inefficient, something basically stupid. So we want to have as accurate cardinalities as possible. Whenever Oracle has an accurate picture of what's going on, that means that Oracle is going to have very accurate cardinalities. And if Oracle doesn't have a very good picture of what's going on, then that means that Oracle is going to have very inaccurate cardinalities. So let's talk about some of the things that have a tendency to sort of ruin cardinality estimates for us. Let's talk about like and using leading wildcards. Let's say that I've got a table called the Bottles of Beer Song. And this table has only one column in it called Song Lyric. And the table spans down for 100 records. Every single record in this table is another verse of the Bottles of Beer song. It's a song that goes 99 bottles of beer on the wall, 99 bottles of beer, you take one down, you pass it around, 98 bottles of beer on the wall. It's a song that we all used to sing on long car trips to annoy the living fire out of our parents. So if we have a table that looks like this, and every single record in this table basically follows the same pattern, you know, X number of beers, bottles of beer on the wall, X number of beers, etc. Question is, how many of these rows are going to contain the word beer? Well, the answer is all of them. All of them are going to contain the word beer. In fact, they're going to contain it multiple times. But if we issue a query to Oracle, if we say select star from Bottles of Beer Song, where song lyric is like %, beer, %, then whenever we get the plan back using dbmsxplan.display, Oracle tells us that, oh yeah, you're going to get 5 records back. Now, that doesn't seem like it's very accurate at all. Let's ask a different question. Let's ask how many times the word hippopotamus appears in the song. So if we issue explain plan 4, select star from Bottles of Beer Song, where the song lyric column is like %, hippopotamus, %. Again, when we get the plan back using dbmsxplan.display, Oracle says, oh yeah, there's going to be 5 records. Well, the truth is, hippopotamuses are not mentioned anywhere in the song. So we know for a fact that 100 rows are going to contain the word beer, because that's how many records there are in the table, and each record corresponds to a verse of the song. And we know that none of those song lyric verses correspond to the word hippopotamus. So the question is, how does Oracle come up with the number 5? Well, let's have a look at what data Oracle has at its disposal whenever it's trying to come up with cardinalities for queries. First thing that Oracle has is table level statistics. All right, and this is going to record things at the table level, such as the number of rows in the table, or the number of blocks that the table occupies, or the average row length of a table. And then Oracle's going to record something called column level statistics. These are going to be statistics that are going to occur at the column level. So if you have 15 different columns on your table, Oracle is going to have 15 different sets of data here. And this is going to record things such as the number of distinct values in a column. It's going to record the high value and the low value of a column. It's going to record the number of nulls in a column. It's going to record the density, which is kind of similar to 1 divided by the number of distinct values, unless you have a histogram, and then things get weird. And it's going to record the average column length. So this is the data that Oracle has at its disposal to try to come up with how many records are going to be returned from where. Question for you is, which of these statistics can help you accurately assess how many records will match the wildcard %, beer, %. Answer is none. Absolutely none of these are going to do you any good. Maybe if you have like two distinct values and you can look at the high value and you can look at the low value, but if you have a normal table with any number of values for the high and low value, you're not going to be able to get an accurate assessment. So the question is, how does Oracle come up with the number 5 in these scenarios? Well, the answer is anytime you have a leading wildcard with the like expression, for example, if you say we're column name like %, or column name like _, Oracle automatically, arbitrarily guesses 5% of the rows in the table are going to meet this criteria. So if you have a query that looks like this, select star from bottles of beer song, where the song lyric is like %, beer, %, and song lyric is like %, hippopotamus, %, Oracle is going to estimate every single time that 5% of 5% of your records in the table are going to be returned, or 0.25%. So the question is, how can we fix this? This is a bad cardinality estimate. Oracle doesn't have an accurate representation of what's going on. How can we fix Oracle's understanding of the situation and let Oracle know how many records are going to be returned from our query? The answer is with the opt estimate hint. The opt estimate hint looks like this. What you do is you type out OPT _ estimate, open parentheses, and then you type out the word table. Literally, this is not a placeholder of any kind. You literally type out on your keyboard TABLE, comma, space, and then you put a table alias right here. So my table here is a placeholder. You would replace that with whatever your table's alias is. You put comma, space, rows is equal to, and then you tell Oracle the number of rows that it should expect from this particular operation. So here, in this case, we've got select. We've opened up a hint, and we say opt estimate, open parentheses, table, comma, Bob's, because Bob's is our table alias here. And we say rows is equal to 100. And in spite of the fact that we're using this like %, beer %, if we use this opt estimate hint, whenever we pull our plan back, Oracle now says, aha, we're going to have 100 rows that come back from our query. And so this is going to help Oracle pick a better execution plan as a result of having an accurate idea of how many rows to expect. Now, you might be looking at this hint and you say, well, this table means that it only works for tables, surely. And you'd be forgiven for thinking that because that seems awful obvious. But the truth is it can actually be used for index fast full scans as well. And an index fast full scan is just when Oracle reads an index instead of reading a table. So if we create an index on our bottles of beer song table, we've got the song lyric column. If we use this opt estimate table hint, we come back with a plan. Oracle is now doing an index fast full scan, and it knows that we're going to get 100 records back. Okay, so we've tried this so far. Let's try a new experiment. Let's create a view. We're going to create or replace view, lyrics containing beer, as select star from bottles of beer song, Bob's, where song lyric is like %, beer, %. Okay, so we've got this view, and it's selecting, basically it's going to end up selecting all the records out of our bottles of beer song table, and we've got that filter. And if we do a explain plan on just selecting everything from our view that we just created, then Oracle comes back and says, you're going to have 5 rows. And that's what we would expect because we've not done any hinting at this point, right? So let's go ahead and add in our hint now. Let's say explain plan for select. We open up a hint here and we say opt _ estimate, open parentheses, table, comma, Bob's, because that was our table alias, comma, rows equals 100. And now that we've added our hint, whenever we get the plan back, well, crap. Oracle still thinks there's only 5 records coming back. What's going on here? Why is Oracle ignoring our hint? The answer is what we're trying to do is we're trying to reference a table that doesn't exist in the current query block. We've got two different query blocks, a query block here, and then a query block that exists inside of this view. We're trying to reach down inside this view and grab a record out of this view, or trying to hint a table inside this view. And Oracle goes, well, I don't know about this table because it's not in the current query block. So what we have to do in order to remedy this situation is we have to use something called a global hint. Global hint looks like this. You say opt_estimate, open parentheses, and you've got this QB1, comma, again, you use the word table here, comma, then you use tab at QB2, and you're like, Kaley, what is all this QB1? What's QB1 and what's QB2 and what's this? These are query blocks. This is your query block after query transformation. This is your query block before transformation, and this is the name or the alias of your table. All right, so query block after transformation, query block before transformation, and the name of your table. You say, okay, how do I get the names of the query blocks, Kaley? Well, whenever you pull back your plan using dbms xplan.display, whenever you provide your format string, if you supply a plus alias, then Oracle adds this new section to the plan down here, and it says query block name. And what this allows us to do is allows us to see which lines of the execution plan correspond with what query block. So if we look here, we see a 1 here, and we see a 1 down here. That means that these two correspond to one another, right? So this corresponds with this index fast full scan here, and this gives us QB1, and this gives us QB2 right here. So here's QB1, the name of our query block after query transformation, and the name of the query block before query transformation. So what we can do is we can just actually take these and slap those into the hint. We have to add a little @ sign in front of this. So instead of using a local hint, let's change our query slightly. We're going to use a global hint now. We're going to say opt_estimate, open parentheses, @ and then I've got my query block name after transformation, comma, table, comma, Bob's at SEL $2. That was my query block before transformation. And then I'm going to say rows is equal to 100. And now when I do this, Oracle understands that, yes, we're going to expect 100 rows from our table. Okay, so that is like and leading wildcards. Let's try something else now. Let's try looking at outlier values. Suppose that we have a table that keeps track of subscriptions of some kind. Maybe it's a magazine subscription or something like that. And we've got a whole bunch of columns on our subscriptions table, but the only column that we really care about is the expiration date of the column. And let's say that we have 100 rows for every single date in this table for the year 2019. So for January 1st, we have 100 rows. For January 2nd, we have 100 more rows. We have January 3rd, we have 100 more rows, all the way down until we get to the very last day of 2019, which is December 31st, and we'll have 100 rows for that as well. So far, I've rattled off 36,500 rows, 365 times 100. Okay, and then let's say that we have 100 customers that have paid us so much money that they literally have lifetime subscriptions. They're going to receive our magazine for the rest of their life. And so what we can do is we can represent their lifetime subscription a number of ways, right? For example, we could just have a null expiration date, and maybe that would represent a lifetime subscription. Or maybe the architects said, no, we don't want to allow nulls here. Nulls are problematic. Null values don't get indexed, and they're tricky to our developers, and we don't want to mess with nulls. So instead of using nulls, maybe they opted to use a date in the future that they know that none of us will ever have to deal with. So maybe they're, instead of using a null value, they're using the date 9,999 December 31, like literally the highest possible date that we can have in Oracle. So maybe for our 100 lifetime lifetime subscriptions right here, we would be using, instead of null, we would be using December 31st of the year 9999. So I've described a situation where we have 36,500 records for January 1st through December 31st of the year 2019, and then we have one final set of lifetime subscribers, and we're assigning them an expiration date of December 1st of the year 9999. Let's add an index onto our expiration date column. Just do a quick create index subscriptions index on our subscriptions table on the expiration date. We'll gather statistics on the table, and then we'll ask Oracle how many subscriptions will expire in the year 2019. So we'll do select star from subscriptions where the expiration date is between 2019 January 1 and 2019 December 31st. And whenever we get this back, Oracle says, oh yeah, you're going to have 105 records. Well, I just told you from the situation that we have that Oracle's actually going to return 36,500 records. So the question is, how did Oracle miscalculate so much here? Well, what Oracle does whenever we have a range-based query like this, where we have a between with a start and an end, Oracle assumes that if it doesn't have any additional help from any place else, it assumes that we have a uniform distribution of data. In other words, Oracle assumes that we have our low value in our column, our high value in our column, and that the data is somewhat evenly sprinkled between your low and your high values. So this is what Oracle thinks is what's going on, but the reality of the situation looks more like this. And this is not even drawn to scale because if it were, it wouldn't fit on the computer screen. But what happens is we have a whole bunch of records down here in 2019, and then we have this huge gap that stretches all the way down to December 31st of the year 9999, and we have only 100 records here that indicate a lifetime subscription. So it's this outlier value here that's causing Oracle to be thrown for a loop. So how do we go about fixing something like this? Well, we can do that with the undocumented opt estimate hint. The local hint version, there's actually a couple of these. You can say opt estimate open parentheses index underscore scan. And again, this is a literal value here. You type in index underscore scan. That's not a placeholder. And then you type in the name of your table. And then you type in the name of your index, and then you tell Oracle how many rows to expect. Now, there's two different versions here. You can either use the index scan or the index filter. You say, well, what the heck? Why are there two? What's the difference? Well, the index scan hint says adjust the number of leaf blocks in the index that we're going to scan. In other words, we are either going to scan a larger or a smaller percentage of the index than what you actually think, Oracle. So you need to adjust your understanding of how much of the index we're actually going to scan. And as a result of using this hint, the cost of scanning the index will increase. The index filter hint, conversely, says only change the number of rows because the number of leaf blocks is actually the same. In other words, what we're going to be doing is we're going to be scanning our index, and we're going to be able to filter out either more records or fewer records than what you think before we actually go and touch the table afterwards. So as a result, there's no change to the index cost scan. The index scan cost is going to be the same if we use the index filter. Here in this case, Oracle's skewed understanding means that it really doesn't understand how much, what percentage of the index we're going to be scanning. So we're going to actually be using the index scan hint here. And we do this by saying opt estimate, open parentheses, index underscore scan, comma subs, because subs is the name of our table alias. Then we say subscriptions index, that's the name of the index on our table. And then we say rows is 36,500. And now when we get the plan back, well, crap, our cardinality didn't go up. Why didn't our cardinality go up? Answer is we got something better than a cardinality change. We got a plan change. Before we were doing an index range scan, and Oracle says, I think I'm going to use an index range scan for this query. And what happens is it looks at our hint, and our hint says, no, Oracle, don't use an index range scan, because if you use an index range scan, you're not going to be pulling back 105 rows. You're actually going to be pulling back 36,500 rows. And Oracle goes, oh my gosh, I don't want to use an index range scan. An index range scan is far too expensive. So it goes, I'm going to do a full table scan. And it does the same cost calculation on the table, and it still comes up with 105 rows. But this is where you can see Oracle starting to understand the situation a little bit better. So what it's doing is it's picking a better execution plan. So we got, this is the end result that we're actually aiming for right here, is for Oracle to pick the best possible execution plan. But let's come up with a better way, or rather, I should say a different way of fixing this. We now have a new cardinality misestimate. Oracle still thinks it's going to have 105 records. I've shown you opt estimate, where we have rows equals some number. And that tells Oracle this is the exact number of rows that you should expect. Conversely, what you can do is you can supply a scale rows number. In other words, that's going to tell Oracle, take whatever your estimate is and multiply it by this number. It could be a fraction so that it decreases. It could be a number greater than 1 so that it increases. Or you can set up guardrails. You can say, don't guess anything that's below this number, or don't guess anything above this number. So one way to be able to fix this would be to use the scale rows hint. Let's go ahead and give something like that a try. So Oracle says, okay, I'm expecting 105 records to come back from our full table scan. Sorry. We know that the actual number of records in a table is 36,500. Therefore, Oracle was off by a scale. If we take 36,500 divided by 105, Oracle was off by a scale of 347.62. So what we can do is we just add another hint to our query here. We say opt estimate, open parentheses, table, comma, subs. I'm actually missing my table alias here, but that's fine. We say scale rows is equal to 347.62. And now when we get the plan back, Oracle's still not picture perfect. Oracle's still not right. We told Oracle we know that the real number is 36,500. Oracle's still saying 36,351. So it's still off by about 149. But that's okay, because Oracle doesn't have to know exact number of records. Oracle only has to be approximate. So the truth is, we just have to sort of be in the same ballpark in order for Oracle to have an accurate idea of what's going on. So this is definitely close enough for us. There were some rounding errors both in the original 105 cardinality that Oracle gave to us and in our scale calculations. The number went out way further than I wanted to put in the PowerPoint slide, but this is definitely adequately close for Oracle to make the right decision here. Okay. So we've talked about like and leading wildcards, and we've talked about outlier values. Let's talk about correlated data and how to go about correcting this. Now, you might be saying, well, Kaley, there's already a documented fix for correlated data. No, you can have things like column groups, and that works if you have data that's correlated and it's on the same table. But what happens if you're joining two tables, and as a result of joining one table to another, you have join skew? If the data exists in separate tables, there's not a documented fix that I know of that allows you to correct those cardinalities. So this is exciting in the sense that this is finally a chance for us to start to correct these cardinalities. And let me show you what I mean. Here, we'll just drum up an example. Let's say that we have an actors table, and it has 1 million actors in it. And we've got a movies table, and we've got 1 million movies in our movies table. Now, the way actors and movies work is they have a many-to-many relationship. In other words, an actor can star in multiple movies, and a movie can star multiple actors. So in order to represent this many-to-many relationship, we have to have a junction table in the middle. So let's just connect actors and movies table with a junction table in the middle here. And suppose that we have 2 million records in our junction table, meaning on average, every actor stars in 2 movies, and every movie on average stars 2 actors. Let's write a query against our setup now. Say, select star from actors interjoin with our junction table on actor ID, interjoin with our movies table on movie ID, and then let's throw some filters on our tables. Let's say where the actor name is equal to Kevin Bacon, and our movie title contains THE. In other words, it could either contain the word the or a word that contains the word the, like the or these or theater or another or whatever. So we have here, we have an extremely strong filter on our actors table. We've limited our list of 1 million records down to just one record. We're talking about Kevin Bacon. And then we have probably an extremely weak filter on our movies table. So we've got a very strong filter. Like I said, we have 1 million records, but we've isolated it down to exactly one actor. If I say Kevin Bacon, you know exactly who I'm talking about. Versus the movies table, I would estimate that maybe a third of movie titles contain THE, right? So even if the word contains the or these or theater or whatever, what usually makes sense in Oracle is to start with your strongest filter. In other words, that would be our actors table here, and then join to the junction table, and then join to the movies table. If we did this, we would start with one row in our actors table, and then assuming join uniformity, we would have 2 rows in our junction table because every actor on average stars in 2 different movies. Okay, so that would give us an intermediate result set when we join these 2 tables of just 2 rows here. So what would happen then is Oracle would take those 2 rows and then join them to the movies table, and we would filter out, say, 33% of them, and Oracle would be left with just 1 record, meaning we would get a final result set of just 1 record. What usually doesn't make sense is to join from our weaker filter over to the junction table to our stronger filter. If you go about things the wrong way, here's what happens. You would filter down to a third of our 1 million records. That's going to be 333,000. Then you join to the junction table. And again, if you're assuming join uniformity here, you would join to 667,000 records. And then you would take those records and join them to the actors table. And, you would take those records and you would join, if you join movies in that junction table, that would give you an intermediate result set of 667,000 records. Then you take those and join those to the actors table where you'd filter down to just 1 record. So your final result set would be 1 record. The difference is you've had to join up 667,000 records. So you're dealing with these larger intermediate result sets. And that's basically the secret of SQL tuning, is just traversing less data. Whether that's by getting the right join order so that you're having to traverse through fewer records and join fewer records, whether that's scanning smaller amounts of data through an index or a table. The secret of SQL tuning is essentially just to traverse less data, right? So you can see here that actors to junction to movies just blows movies to junction to actor join water. This join order actually blows this join order out of the water. There's no comparison. You'd much rather deal with 2 records than you would for 666,666. But question for you, what if Kevin Bacon acted in all 1 million movies? What if Kevin Bacon was the busiest actor on the planet, and literally the entire junction table consists of Kevin Bacon and another actor, Kevin Bacon and another actor, Kevin Bacon and another actor, movie 4 is Kevin Bacon and another actor, movie 5 is Kevin Bacon and another actor, etc. In that case, if we were to join from the actors table to the junction table to the movies table, we'd start with 1 row here, and then we would go and we'd pick up half of this table. We'd pick up 1 million movies because Kevin Bacon is starred in all 1 million movies. And so we would have this intermediate result set of 1 million. Then we take those 1 million records and we join them to the movies table. And that would allow us to filter out a third of those. So we'd be left with a final result set of about 333,000. what normally doesn't make sense, but might actually make sense here, is if we go about things the opposite way around. If we go from the movies to the junction table to the actors table, movie says we filter down to 333,000 records first by applying our allegedly weaker filter, but then we would, assuming join uniformity, we could join to the junction table and pick up 667,000 records. Then we take those 667,000 records and we'd filter down to just one row in the actors table. And so we'd have a final result set of 333,000 records. So in this case, because of our join skew, it actually makes sense to go about things the opposite way around, to actually start with the allegedly weaker filter, because as a result of just join skew between two different tables, we would end up blowing our record count out quite a bit. The problem is Oracle always is going to assume join uniformity. And so Oracle's without the help of any kind of adaptive or reparsing or something like that, Oracle's always going to give us this plan right here. So the question is, how can we fix this? Well, with the undocumented opt estimate hint. Here's what the local hint of the version looks like. We've got opt underscore estimate, open parentheses, JOIN, comma, open parentheses, and then you can just start listing table aliases. So table A is an alias, table B. You can list as many of these as you want. You cannot list one. Obviously, it doesn't make sense to list one table joining to, I don't know what, just you have to have more than one, right? Because it's a join. That's the whole point of a join. But if you have more than one table here, then you're good. You can list as many as you want. You can list 2, 3, 5, 7, 99, etc. And you just say rows is equal to 99. Or however many rows you want to tell Oracle. So if we incorporate this join estimate hint here, we tell Oracle, hey, when you join A to B, you're going to end up with 1,000,000 records. What happens now is you can see that Oracle actually paid attention. It goes, okay, if we join this to this table, we're going to end up with, it says 100, it says 1,000, 1,000. So this is 1,000, and in this case, an additional 1,000. So this is actually 1,000,000. So don't let that confuse you. Oracle says we're going to have 1,000,000 records when we join the actors and the junction table. Whereas if we join to the movies table, Oracle's filter is still a little bit off here. So we can actually correct this with a table version of the hint. So if we say opt estimate open parentheses table, comma C, comma rows equals 333,333. When we do this, Oracle says, Oracle's actually done the exact thing that we wanted it to. Oracle started with the movies table and then is going to join it to the junction table, and it's going to join the result of that to the actors table. So you can see that we've got 333,000 for the movies table, 667,000 records for joining the movies to the junction, and then we finally get down to the one record for the actors table. So there are variations of the opt estimate hint. You can tell Oracle that I want to change my estimate for a table, or I want to change my estimate for an index scan or an index skip scan, an index filter, a join, nested loop join, index scan, nested loop index filter, a group by, a query block, and I think we talked about all the variations of the rows. We talked about rows, scale rows. You can set up min and max, and you can combine scale rows with min and max. In other words, it doesn't make sense to specify this is the exact number of rows that you're going to have, but you can say scale the number of rows and don't adjust your guess if it's below this, or adjust your guess if it's above this. So at this point in the game, usually I have questions that are asked. This time I've actually pre-recorded a series of questions that are probably the most common that I get for this. And that the first question is, how accurate is close enough? This is the question that I probably get the most. Oracle's usual answer is roughly the same order of magnitude, right? So if your estimate says 30,000, and your actual number of rows says 90,000, then you're probably you're probably in the right ballpark. You probably have a reasonable execution plan. Versus if you have 30,000 and the actual number is 300,000, okay, maybe it's time to try to adjust your cardinality. Another question that I usually get is if there are multiple cardinality misestimates, which one should I go after first? And the answer is you want to go after the earliest possible in the join order, because that could cause other cardinality misestimates to sort of cascade. That could correct other problems later on. Okay. Another question that I usually get is how do I find actual versus estimate cardinalities? And this is a great question. There's two different places really that you should look. Number one is extended row source statistics. If you do an alter session, set statistics level equals all, or if you go about using the gather plan statistics hint in your query, whenever you pull back a plan, you can specify for your format. You can say all stats last. And what Oracle will do for a serial plan is it will show you two new columns. It will show you the expected number of rows, and it will show you the actual number of rows. It'll abbreviate these as E rows and A rows. Another place that you could look would be a SQL Monitor Report. If you generate one, you can see that over here, Oracle has the estimated number of rows. So these are the number of rows that Oracle estimated, and over here, you can see the actual number of rows that are returned from each step in the plan. So that's another place that you could look it up. I'll do another one. Why do tables that are joined in a nested loops fashion always seem to estimate just one row? The answer is whenever you have this is your inner child for a nested loop. Whenever you have your innermost child for your nested loop, Oracle is actually estimating the number of rows that it's going to pick up per iteration. So what Oracle is saying here is I'm going to get 10 records as a result of scanning T4. And then I'm going to do a nested loops iteration. And for each iteration of the nested loops, Oracle is estimating that it's going to pick up one row, meaning that this nested loop will come up with 10 rows. And then this nested loop will invoke this other nested loop and do table access by index row ID. And again, this will come up with one row. So we're going to have a final result set of 10 rows. Those are all the questions that I have. I wanted to say thank you for hanging out with me. And as my thank you gift to you, I'd like to give you a copy of the notes and the slides. I have a lot of people that ask me for, Kaley, could you please have a copy of the slides? Or Kaley, I'd like some notes on this. I've prepared an 11-page PDF that you can have absolutely for free. All you have to do is just go to tuningsql.com/undocumented to claim it there. It's all about the opt-estimate hint. It's 11 pages of extremely difficult to find information. So feel free to grab that. And that's all I've got. So I want to say thank you for attending, and I appreciate you.
Yeah, if anyone have any questions, please post in Q&A chat. And thanks, Kaley, for your very insightful session. It's awesome. Thank you.
Awesome.
And anyone have any questions? We'll wait for some time and then see if anyone questions.
Recording available.
Yes, the recording will be available and will be posted in the portal, and you can view the recording. Yep.
Awesome stuff. Thanks.
Okay. Thank you so much for attending, and thanks for your time, Kaley, as well. And this was a great session. Thank you so much.
Awesome. Thank you. Take care.
Thank you. Take